So yeah, today I'm going to talk about space junk, and the message is, wherever humans go, we leave a mess, and we always start off thinking, well, this new place we're in, it's enormous. We can throw all our garbage away and it will never overflow. And as always, that turns out not to be the case. So I'm going to start trying to share my screen. Here we go. And share and presentation mode. So hopefully you can all see that.
Yeah, that's
and so this is just an illustration of lots of different satellites to show you they're all different shapes and sizes.
I'm really sorry. I think actually it's black right now.
It's black? Oh no, that's not good.
Okay.
Can you see anything now?
No, it was
all right. Let's try with this. Can you see that?
Yeah.
All right, so I'm not going to go to presentation mode. That's the solution. Let me just reorganize the size of the... I'm going to stop sharing for a second. This is a new problem that I haven't had before. But we will get through it. All right, so you can see that, yeah?
Yeah.
And still?
Yeah.
Okay, great. So the very first satellite was launched in October 1957, the Soviet Sputnik. But the Soviet Sputnik is not the first object in the catalog of orbital objects. The first catalog number 1 in the space satellite catalog is actually the rocket stage that put Sputnik in orbit. And so the very first thing in the catalog is a piece of space junk. And so Sputnik was this 83 kilogram satellite. Then it went up with this 7-ton rocket stage and also a nose cone. And the trick is that when you launch a satellite into orbit around the Earth, the rocket that launches it, multi-stage rocket, punches up through the atmosphere for like 3 or 4 minutes until it's above the atmosphere. And then it spends another 5 to 10 minutes going sideways, building up speed to orbital velocity, to 17,000 miles an hour or so. And then the rocket engine switches off, and the rocket and the satellite are in orbit. They can fall all the way around the Earth without using any more fuel. But every time you launch a satellite like that, you've launched a rocket stage as well. And so you've got a piece of junk unless you do something about it. And so, there are a lot of satellites in space. So I want to just give you a sense of what's out there, and then we'll focus in on the junk aspect. So we have communication satellites. We have satellites that image the Earth. We have what are called signals intelligence satellites, which do like phone taps and measure the properties of military radars. There are technology satellites that are testing new components that are going to go on more expensive later satellites, and also ones that are there basically for education to train aerospace engineering students in making satellites. Of course, there are navigation satellites. GPS is ubiquitous now. There are science satellites. A lot of people I meet who are not in the space game sort of think that most of what goes on in space is to do with science, but actually science satellites are a pretty small fraction of what's happening in space. And then there are spaceships like the Soyuz spaceship you can see here on the right with astronauts on board. Those too are satellites. And so we've got our own little artificial aluminium titanium asteroid belt. There are about 4,800 satellites now operating in orbit around the Earth. And some of them are in low orbit, mostly going from pole to pole, just a little fuzz around the Earth. And then you see this ring further out that is the geostationary orbit, 23,000 miles from the center of the Earth, and a lot of the communication satellites sit in that special orbit. And all of these orbits, unfortunately, are full of the trash that has come from these launches. And to show you why it might be a problem, here's a picture taken earlier this year of the robot arm on the space station, and on the right, a close-up showing what looks like a bullet hole in the arm that was caused by a piece of space debris, very small piece of space debris, but remember, everything's traveling at 17,000 miles an hour in different directions. And so if you get hit by even a very, very small piece, a centimeter or so, it's really going to hurt. So I wanted to give you a sense of the different, what is the debris that's up there? What's the population of space debris? And since Sputnik, the radars have cataloged over 49,000. As of today, the highest catalog number is 49,329. Now, a lot of those have re-entered the Earth's atmosphere since they were launched, but there are still over 22,000 objects that are being tracked every day by the US Space Force. In addition to those 22,000 objects that are maybe 10 centimeters and up in size, we think there's about 1 million objects that are a centimeter or bigger, and maybe 1 billion objects that are a millimeter or bigger. So there's an awful lot of stuff that's too small for us to track. But I'm going to focus on the stuff that we can actually observe. And so of those 22,000 objects in space, and I've shown a few examples in the pictures here, I'm not going to go through all the little details, but this is mainly to show you that every one of these 22,000 objects, we have pretty much some idea of what they are. And so, yeah, there's about 4,700, 4,800 active payloads, almost as many dead payloads, because when a satellite stops working, it doesn't fall out of the sky, it keeps on orbiting. And it becomes space junk. There are these empty rocket stages, about 2,000 of those. There are various trash that we've thrown away as part of a launch, about 1,700 different kinds of trash, from jettison motors, canisters, insulation blankets that have come off, a few nuclear reactors that got jettisoned. That's fun. And then, a few hundred pieces that we're not quite sure what they are. They just came off their parent satellites. In addition to the deliberately jettisoned stuff, there's about 11,800 objects that are what I think of as mostly accidental debris. In particular, the biggest single category here is there's 4,600 objects that are shrapnel from old rocket stages that had fuel left over. And after a few years in orbit, the fuel and the oxidizer connected, and the whole rocket stage blew up into hundreds of pieces. And so that's a real problem in generating space debris. The next biggest contribution is not so accidental. It's the result of anti-satellite weapons tests. And in particular, the Soviets tested some anti-satellite weapons in the 60s and 70s. And China did a big test in 2007 that has a lot of debris still in orbit, almost 3,000 pieces from that launch alone still in orbit. There are accidental collisions. Accidental collisions have resulted, right now there's about 1,400 pieces from accidental collisions. That's relatively, so it's only about 10% of the debris population, right? But the problem with accidental collisions is that the rate of collisions goes as the square of the total number of satellites you have. So all these other objects go kind of linearly. So if you have 10 times as many satellites a few years from now, and indeed we are expecting that a few years from now there will be 10 times as many satellites, then there will be 10 times as much of this other kinds of debris, but there'll be 100 times as many collisions. And so even though the collisions don't dominate now, we expect they will in the future. And so that gives you a sense of the different sorts of things we're talking about when we talk about space debris. And it's in all kinds of different orbits. So, one of the main questions we asked is, what's the inclination of the orbit? Does the orbit go around the equator, like this purple line? Or around the poles, from pole to pole, like this blue line, or somewhere in between, like the International Space Station, which is in a 51-degree orbit. And so whatever the orbit is, the center of the Earth is at the center of the orbit. So I just want to remind you, you can't do an orbit like this yellow one, which sort of zips a lot around some high latitude. It has to be a great circle where the center of the Earth is at the center of the orbit. So you can tilt this circle, but you can't move it up and down. Oops. And most of the satellites are going from west to east in the same direction that the Earth spins, except the ones in polar orbit, but all the other ones are going. And the thing is that if you launch, say, from Florida, right, Florida is moving toward the east as the Earth spins at about 1,000 miles an hour. And so you get a free 1,000-mile-an-hour boost if you go in the direction that Florida is moving. So launching backwards, going westward around the world, is really rare, and there are only a few satellites that do that. And satellites are all different sizes. Some of them can be very small. One of the common kinds of satellite that's launched now is called a CubeSat. The base CubeSat is 10 centimeters on the side. It's a kilogram. You can hold it in your hand, called a 1U CubeSat. A bit more common is the sort of satellite that this guy on the bottom right is holding, a 3U, that's sort of 3 of those cubes stuck together, maybe with some solar panels and instruments. But still, that's only a few kilograms. It's pretty small. The biggest satellite is the International Space Station, the biggest artificial satellite. That is over 400 tons. And so, so that's the range. The satellites range from a kilogram to 400,000 kilograms. So there's a lot of variety. So why is the orbital debris a problem? So I want to introduce you to this satellite, Iridium 33. It's about half a ton. It was, and it orbited the Earth for about 12 years, providing cell phone service. And it one day met this satellite, an old Soviet or Russian communications satellite, military communications satellite, that had been junk since 1995. It had died. And almost 500 miles over the Arctic, they hit each other at 26,000 miles an hour. And so I want to give you a sense of how much energy that involves. And so my unit of ouch, that hurts is, imagine that you are hit by a 1-ton truck going at 100 miles an hour. You have a sense of what that would be like. You want to avoid it. And that is actually about a megajoule of energy, 1 million joules. This collision of 2 half-ton satellites hitting each other at orbital speed had an energy 54,000 times the energy of that truck collision. 54 gigajoules. So that's an enormous amount of energy to concentrate in a couple objects the size of a vehicle. And so what that happens is that you turn both satellites into small shrapnel clouds that pass through each other still at orbital velocity, and you turn each satellite into a cloud of debris that moves along the same orbit. And you end up with thousands of pieces of debris that spread out along the orbit, and then due to various orbit math that we can talk about if you like, spreads out into a whole shell going around the Earth. And then because of drag with the atmosphere, the shell slowly gets thicker. And so you quickly fill space with all of this stuff. I'm actually going to skip that. Even small pieces of debris are dangerous. Remember, the key thing here, right? The reason why this is so bad is because kinetic energy goes like the square of velocity. 10 times as fast, 100 times more energy. And so when you're going at these incredible speeds of 17,000 miles an hour, even a tiny piece of energy is bad. So a little piece of space junk hitting your satellite is like, again, a 1-ton truck at 1,000 miles an hour. And so even if it doesn't destroy your satellite completely, like this incident in 1996, it'll break pieces off, even if it hits a glancing blow. So that's one problem that space junk gives us, is a danger to other space traffic. And the more space junk there is, the more likely that your very expensive satellite is going to be hit and possibly even destroyed. But there's another kind of problem, which is that space junk can crash to Earth. When it re-enters, it enters the atmosphere at 17,000 miles an hour. So now, what happens when we do that is you get very hot and you melt. And in fact, just a couple of days ago, there was a Russian satellite that had failed, and it re-entered the upper atmosphere over Michigan. And I got all kinds of calls from media who wanted to know what this thing was. A spectacular fireworks display in the sky as this thing broke up about 50 miles up, and everyone in Detroit was sort of looking up and so what's that? Oh my God. And some of the YouTubes are quite funny. People are really freaking out. But actually, probably none of it reached the ground. It probably completely melted all the way through. And yeah, you contribute some molten aluminum to the upper atmosphere, and in small amounts, that's probably not a problem. We're starting to worry with the increase in space traffic that even that could start to be an environmental issue. But the bigger worry is if you have a big satellite re-entering, the re-entry is so fast, only a few minutes, that it doesn't have time to melt all the way through. And the denser pieces of the satellite will survive and hit the ground. And famously, back in 1979, America's 75-ton Skylab space station re-entered, and big chunks of it hit, fortunately, the desert in Australia. And that made people go, yeah, probably we shouldn't do that. Probably we shouldn't throw large chunks of metal at high speed towards people on the ground. And so since then, the biggest spacecraft all have rocket engines that can be used to actively re-enter them while they're still alive and shove them down at a particular place on the planet. So if you just let something orbit the Earth and it's skimming the Earth in a circular orbit, getting lower and lower and lower and lower, at some point it'll break up and melt, but you don't know exactly when that's going to be because you're just skimming this upper atmosphere going round and round the world every 90 minutes. And if you're even 20 minutes off in your prediction of when it's going to break up, you're several continents out. So you don't know where it's going to come down. But if you have it in a higher orbit and you go, okay, I'm going to fire the engine to change that orbit to elliptical so the opposite side of the orbit is inside the atmosphere, you know exactly where it's going to hit the atmosphere 40 minutes from now. And so you can target it to come down in the middle of the South Pacific and where it's not going to hit anyone except maybe a few penguins. And so we avoid these accidental reentries, and it's mostly not a problem at the moment. There have been a few really bad cases. The Soviet Navy was a huge fan of nuclear reactors, so much so that it put them on their satellites. And so you had satellites with radars tracking the American Navy that were powered. The radar needed a lot of electricity. It was powered by a nuclear reactor. And then at the end of its life, it would boost up to a 1,000-kilometer orbit. But Cosmos 954 in 1977, its engine failed. It got stuck in low orbit, and the whole thing re-entered over Canada. And so now you may know that, some space probes use nuclear power, like the Voyager probes to the outer planets use a thing called a radioisotope generator, which is basically just a warm lump of plutonium that you're running a thermocouple off. And so it's not critical. It's not a nuclear reactor. It's just a thermoelectric generator using radioactivity. That's not what we're talking about here. We're talking about a full critical nuclear fission reactor in space falling on your head, and so they had this massive cleanup effort in around Great Slave Lake in Canada, picking up radioactive debris. They found like beryllium control rods from the reactor melting holes in the ice due to their radioactivity. That was not good. And people have been even, hit by space debris, but not seriously. So this lady was hit by this twisted piece of metal that had been going at 18,000 miles an hour, but when it entered the atmosphere, it slowed down rapidly and was only going probably a few tens of miles an hour when it hit her shoulder. And so she had a mild bruise, but that was about it. And that's the only person that we know of that's actually been hit by space junk. But we do see things survive to the ground, in particular, big empty fuel tanks sort of float down on the atmosphere. And so here's some cases from around the world where propellant tanks have landed in someone's field, and they're going, whoa, what's this? And so there have been some big uncontrolled reentries in the many tons case, but very rarely recently. We still get 8-ton things falling down. And so this is a plot of how many tons the thing was versus when it re-entered. And you see, there's been a few over the decades, but really not many above 10 tons. The exception is that in the past couple of years, China started launching a rocket called the Long March 5, and the Long March 5B rather. And the Long March 5B leaves a 20-ton rocket stage in low orbit that re-enters at some unpredictable place. And they've done this twice now, and they got lucky once and unlucky once. So the unlucky time, this rocket stage entered over West Africa, and there are pictures of like 30-foot long metal rods that smashed into some poor guy's roof in villages in the Ivory Coast. And so fortunately no one was hurt, but there was property damage in various villages. So we don't like big things re-entering. Small things re-entering are probably not a big deal. Now I want to look at how things are changing. And this plot shows you how many working satellites there are in space as a function of time. And so we think of the 1960s as being, the space race and so on. But back in the 1960s, there were only about 100 working satellites in space. And as we got into the 2010s, that was more like 1,000. And look at how steeply this curve is going up now. It's going almost vertical. There are now almost 5,000 working satellites. And that number, I have to, every time I give this talk or talk like this, I have to change the graph because it's just changing so quickly. And I've divided it here into 3 types of working satellites. And so the pink color at the bottom is satellites that are working but don't have the ability to change their own orbit. The Hubble Space Telescope is one of these. The Hubble Space Telescope doesn't have a rocket motor. It just keeps orbiting the Earth. And if we want to reboost it, we have to dock with it with a space shuttle or something and boost it back up because it can't do anything on its own. And so if you're a working satellite that can't change its orbit, as far as everyone else driving around in space is concerned, you might as well be space junk because you're just a loose cannon. The dark red color are the active satellites that can change their orbit. And so what you can see here is that they have been an increasing fraction of working satellites, starting in the 1980s and going on, was more and more common for your satellite to be able to change its orbit, which is good. The cyan color is a particular set of satellites called Starlink, launched by SpaceX starting in 2019. And the Starlink satellites are meant to provide cheap spaceborne internet. And he's launched a couple thousand of them. Elon Musk has launched a couple thousand of them, and they're planning to launch as many as 30,000 of them. And so these Starlink satellites and similar constellations are going to dominate the space population pretty soon. But now I want to, so I had 3 colors on the previous graph. I wasn't including the space junk. That was just the working satellites. If you add the space junk in, those 3 colors from the previous graph become a pretty small icing on the cake of the of all the different kinds of space junk. And so we have in brown satellites that used to be working but are now dead. In purple, rocket stages. In orange, random litter that people have thrown off of satellites, like nose cones and so on. In green is the debris from exploding satellites and weapons tests and things like that. And I called out in yellow and black 2 specific incidents. In 2007, the Chinese weapons test, and in 2009, the collision that I told you about a few minutes ago, the Iridium and Cosmos satellites that collided. And you can see that when those events happened, there was just a really huge jump in the overall amount of space junk that we knew about. So it only takes a couple of incidents to really increase the amount of space junk. But that's sort of averaged over the whole of space. Oh, and this just does the same plot, but with mass instead of number of satellites. Just counting, there's about 10,000 tons of rubbish in space right now. Well, okay, so actually a bit over half of it is rubbish, a bit under half of it is working satellites. And how long is this stuff going to stay up for? It depends on how high it is. So you think of space as empty, but actually outer space has a little bit of gas in it, a little bit of atmosphere all the way out. And it gets thinner and thinner and thinner the higher you go. If you're only a few hundred miles up where the International Space Station is, it's still, it's a good vacuum, right? But if you're going through it at 17,000 miles an hour, it's another one of these squared things. If you're going twice as fast, the headwind slows you down 4 times as much. And so even a very, very thin gas is a significant headwind if you stick your head out of the car as you're driving down the motorway at 17,000 miles an hour. And so in low orbits, that causes the objects to spiral in and eventually burn up in the Earth's atmosphere within a few weeks to a few years. And it turns out there's a fairly sharp change around 600 kilometers. If you're below 600 kilometers, what I'm showing here on the vertical axis is how long did my satellite stay in space after I stopped using it, after I switched its engine off? How long did it take for the atmosphere to bring the satellite down? And if it's below 600 kilometers, the answer is less than 25 years. And in some cases, if you're way low down, less than a year. But if I'm above 600 kilometers, I might have been up there for 50 years already. And in many cases, certainly at 1,000 kilometers and up, I'm probably going to be up there for centuries, unless we do something, unless we send space garbage trucks up to remove it. And so we talk about, in the space game, we talk about low Earth orbit. And low Earth orbit is all of this plot. It's between about 200 kilometers and about 2,000 kilometers above the Earth. But really, I think we have to start making a distinction between lower LEO, lower low Earth orbit, and upper LEO. And so lower LEO, below 600 kilometers, things don't stay up for very long. There's a natural self-cleaning oven kind of thing that the atmosphere has that cleans the debris out. Above 600 kilometers, upper Leo. If you put junk there, it's going to stay there. So what I'm going to do is I'm going to show you 4 plots of big and small satellites in upper and lower Leo. And I'm going to start off with the small satellites in upper Leo. So the ones that are going to stay out there for a while, and they've been accumulating for 60 years, and there's now 12,000 small objects. By small, I mean less than 100 kilograms. And I'm using the same color scheme as before. You'll notice you don't see the red active maneuverable satellites, a few of the pink active satellites, and most of this is junk. So there's 11,000 objects, mostly junk. And after those bad events in 2007 and 2009, not much change in the past dozen years or so. There's a fairly stable amount of space junk in upper Leo. Now, the amount of big stuff in upper Leo, above 100 kilograms, is increasing, and it's increasing gently, but it's increasing. And again, the red and the pink are the working satellites, and the other colors are junk. And so you can see that even for the big objects, it's mostly junk in upper Leo. And the reason I show you this is because the story is so completely different in lower Leo. In lower Leo, if we look at the small objects, a dozen years ago, these colors, the green and the orange, are junk or debris. So same story, much lower level. Changes rapidly with time because things don't stay up for very long. And then in 2015, you saw a change. And this pink color, which is the active satellites that can't change their own orbit, is now completely dominating the population of small objects in low orbit. And we call this the CubeSat revolution. That this ability of people to build very small satellites, even on a university budget or on a startup company budget, mean that hundreds, in fact, thousands now of these very small satellites have gone into orbit and are working in orbit. So that has completely changed this graph from 2010 to 2020, now completely dominated by CubeSats and not by debris. And then if you look at the bigger objects in low Earth orbit, a similar story just in the past 2 years. The cyan color is Starlink, and Starlink satellites are now completely dominating the population of objects that are both big and low. So when the first Starlinks went up and astronomers started complaining, hey, these are really bright, get them out of our sky. Elon said, well, but you know, there's 20,000 objects in orbit. We're just launching a few more thousand. That isn't going to make any difference. Yeah, but it turns out that those 20,000 objects are mostly in higher orbits and they're mostly small. For big, low objects, Starlink is already completely dominating the population. And big, low objects are the objects that are going to be bright enough for you to see from the ground with your naked eye. And so Starlink is already dominating the population of things that are bright. And only 5% of the constellation is up so far. So it's going to be huge. So that's what I want you to take away from those 4 plots, is that upper Leo, things aren't changing much. It's mostly debris. It's fairly stable. Lower Leo, we are seeing transformational change in just the past few years in the space object population. It's no longer dominated by junk. It's dominated by active satellites. Because if those active satellites start hitting each other, pretty soon it'll be dominated by junk again. So we have to be careful about that. So where is the junk? I already said a little bit about that. I'm going to talk about the height of the junk above the Earth. And this shows, again, this is a different color scheme. This is green for satellites that are working, red for satellites that are dead, and black for everything else. It doesn't matter. They're all showing the same pattern, which is that there's a lot of satellites between about 300 and 1,200 kilometers in low Earth orbit. And then there's a gap. And the gap is because of the Van Allen belts, the radiation, That means if you're going to have a satellite in that higher altitude range, it's going to be more expensive because you have to protect it against the radiation. But there's this very valuable orbit at 36,000 kilometers, the geostationary Earth orbit, that has a lot of satellites in it. And so to a first approximation, everything in space is either in low Earth orbit or it's in geostationary. And then there's a sort of secondary peak here where the GPS satellites are. And this map is a little more complicated, so I'm going to take you through it. Again, same thing. Green is working satellites, red is dead satellites, and black is junk. And from left to right are things that are near the Earth to things that are far from the Earth. It's a log scale. And so we have the ISS in low orbit, we have the GPS satellites, the geosatellites, and then on the right, the moon. From bottom to top is the orbital inclination. What do I mean by that? The things at the bottom are spinning around the Earth in the same direction that the Earth is spinning. They're going eastward. The things at the top, if there were any, would be going the other way around, westward. And the things in the middle at 90 degrees would be going from pole to pole. And so what you can take away from this graph is that most things in low orbit are between 50 and 100 degrees. They're going pretty much over the poles. And most things in high orbit are in 0 to 20 degrees. They're going around the equator. And there's almost no satellites going the wrong way around. You see, there's like 4 satellites here and some debris that's going toward the west. So a question for the audience I'll ask you at the end is who is foolish enough to launch satellites going the wrong way around? Why would you do that? Because it requires a much bigger rocket for the same size satellite. There's this huge concentration here that I marked SSO, Sun Synchronous Orbit, is a particular set of orbits that's very popular, where a lot of the Earth imaging and weather satellites are. And there's also a lot of debris there because that's where China blew up its anti-satellite weapon, and they really did it in the worst possible part of space. This is just showing the different countries. Blue is America, red is Russia, purple is Europe, green is China. And what you see is little stripes, right, at given inclinations. And that's because the cheapest way to launch something into orbit is to launch due east from your rocket side. And if you launch due east, you end up in an orbit whose inclination is equal to the latitude of your launch site. And so at 28 degrees, there's a bunch of blue. Actually, there isn't. There should be a bunch of blue American ones. I don't know where they've gone. But here at these red stripes are the high latitude launch sites from Russia. And then there's special orbits. And the European stuff are down at low inclinations here is from the French Guiana launch site that's near the equator. And so you can read, there's all kinds of information encoded into these maps. I just want to show you a zoom in to the geostationary orbit. The geostationary orbit is when you take exactly 24 hours to go around the Earth. And so if you go around the equator in 24 hours and the Earth is spinning every 24 hours, you stay above the same spot on the Earth all the time. How precisely do you have to be at a particular height to take 24 hours to go around the Earth? Very precisely. You see that all of these active satellites are within about 1 kilometer of the magic geo height. After they're retired and dead, we boost them up to higher orbits. But when they're active, they have to stay really exactly. They have to be at 35,786 kilometers around the Earth. If you put them at 35,787, they're going to start drifting. So the math is important here. You really have to get it right. And this is the sun synchronous orbit I was mentioning, where at a few hundred kilometers and inclinations of like 97, 98, 99, which mean a little bit west of north. So you're going around the world, mostly polar, a little bit west, and for a magic, complicated reason that encoded by this equation that I can explain if anyone really wants to know, you want to be on this purple line. And you see all the active satellites in this picture are near the purple line and not, for example, top left or bottom right. And so that's a very valuable orbit. And all the black stuff here is the Chinese anti-satellite junk, where they fired a missile and blew up a satellite that was in this orbit. And so that's why everyone was so pissed at the Chinese for that particular weapons test, because it really increased the danger of collisions in this particularly popular orbit. So what are we going to do to fix the problem? There are various ways to get rid of your space junk. One way is to not leave the rocket stages in orbit. So the obvious thing to do is to restart your engine to bring the stage back down after deploying its satellite. But that's more expensive. A restartable engine, it's actually hard to restart rocket engines in space, so it's more expensive to have it restartable than not. But that's why we didn't do it in the 50s, 60s, and 70s. But mostly now, rocket upper stages are deorbited. They bring them back, smash them over the ocean. Now, you probably are familiar with the fact that SpaceX brings back its first stages and lands them and reuses them, which is cool. But it's a little harder to do that for the upper stages because they're going so much faster. The reentry heating is much bigger. And so it would be much more difficult to recover an upper stage. Starship, of course, is going to try this. We'll see if Elon can get it working. But right now, upper stages are not recovered and reused, but they are deorbited to stop them being space junk. And the same can be true of the dead satellites. Back in the 70s, they mostly didn't have their own engines. Big ones nowadays most do. And so if you're a responsible space user, you re-enter them over the ocean at the end of their mission. Or if they're in high orbit, it's too hard to bring them all the way back down, but you can move them up like we do with the geostationary satellites to what's called a graveyard orbit, a less busy orbit that no one cares about as much. In the future, I don't think that's going to be good enough. In the future, I think we're going to have to actually bring down all the old satellites that we left up there. And I'm hoping that we're going to find a way to tax satellite operators to fund a fleet of space garbage trucks that are going to bring the satellites back. Another thing is that you get these things like this adapter here. This is a diagram of an Ariane rocket with two satellites, a rocket stage, and a little cap that goes over the lower satellite so you can put the upper satellite on it. And so that cap gets ejected into orbit. You could imagine that instead you could put it on a hinge to keep it attached to the rocket stage and so have one less separate piece. That'd be a good thing to do. They're not doing that yet. Another problem is these rockets that blow up with leftover fuel. Particularly bad one is this little thing. It's only a couple of feet across. It's an auxiliary motor that the Russians used in its upper stages, and they fire these little motors to get the stage going again, and then they jettison them. And then 5-10 years later, they blow up with the leftover fuel in them. So you really need not to have these kind of rocket stages that have leftover fuel that isn't vented. You've got to make sure that you do what's called passivation, a horrible noun, but what it means is make the object passive, get rid of all the stuff that might blow up. And so people are moving toward that design. Sometimes batteries blow up. There's a lot of energy in batteries. And so there's a particular kind of satellite that every now and again tends to blow up its batteries and cause a lot of debris. So, we're not quite sure why, and they're trying to figure out how to make that stop happening. A really bad thing is a self-destruct system. This was particularly common on a Soviet missile warning satellite called Oko. They were worried that the satellite might re-enter over America and survive, enough stuff would survive that the Americans would figure out what the satellite was made of and steal all their secrets. And so they designed a system that would blow it up as it re-entered the atmosphere. Unfortunately, this self-destruct system had a bug, and while the satellite was still in orbit, but 5 years after it had stopped working, it had a tendency to go bang without them commanding it. And so a lot of these things created a lot of debris. And the solution is easy. Don't put self-destruct. Don't be so paranoid. Don't put self-destruct systems on your satellites. Similarly, anti-satellite weapons leave a lot of space debris in orbit. Here is an American one on the left, where they put a missile on an F-15 airplane, fired it up, and destroyed a target satellite. Here is a Russian satellite that released a lot of shrapnel, shotgun pellets to destroy another satellite. There's a lot of this left over in orbit from like 50 years ago even, which is really bad. And the solution, again, is easy. Don't do that. Really don't do debris-generating anti-satellite weapons. It's not good because you want to use space too. And so there are all of these different improvements that we can make to the way that we use space that will decrease the amount of debris that we generate. But it's not enough. Even with the debris that's up there already, if we don't do anything, that debris will eventually hit each other and have a runaway Kessler effect that will turn all of Earth orbit into Saturn's rings, but made of aluminum shrapnel. And so we really need to get rid of the junk that's up there already. Let me see, I just want to see if there's any of these. No, okay. So I think I'll wrap up there. And just leave that as my final slide of like all the things that you shouldn't do if you want to be a good citizen of outer space. I'm happy to take people's questions.
Thank you very much for the talk. It was really interesting to see where all the debris originated from and the whole kind of picture behind it. We had some questions from the audience, and it is, should we fear a Kessler effect in the near future?
Well, the thing about the Kessler effect, right, is it's not like in the movie Gravity where it all plays out in about 30 minutes. It's more like 30 years, right? That it's the usual kind of environmental problem where it's not like you wake up one day and suddenly the environment's gone to crap. It's that you slowly drown under all of this horrible stuff. And so the math suggests that the Kessler cascade is slowly underway, but it's at a very early stage. And so we can stop it if we're very careful and if we start cleaning up. Particularly the thing that triggers most of the Kessler is when, like the thing we had in 2009, when two big satellites hit each other, because that's what generates the most chain reaction kind of debris. And so we really need what's called active debris removal. We need to go up and remove the biggest dead objects in orbit.
Can I ask, how optimistic are you that we will proceed sensibly?
Not terribly. I think again, I predict it's pretty. We've had enough of these things already, right, on Earth. The pattern is we wring our hands but don't actually do anything until it gets really, really bad, and then we scramble to do something that's a bit too little, too late. And so I think once it starts hitting the bottom line of the satellite communications companies, once we have a couple of Starlinks that get hit by space debris and lost and so on, then the corporations will go, oh, we're losing money because of this. We really have to get serious now, and things will happen. But and then there'll be a mad scramble, and we'll probably manage to kind of clean it up just in time. But it's gonna be ugly for a while. That's my prediction. I mean, it's a pretty easy prediction given on every other environmental problem we've ever had, ever.
So what do you think of space debris removal companies like Astroscale or CareSpace? And like, which one do you think has the most future?
Yeah, this is very exciting. We're at the stage now where there are companies whose business model is, let's clear up this debris. And it's not, what doesn't exist yet is the actual market that's going to let them make a profit, right? Right now, they're experimenting with which technology is the best. So, for example, Surrey Satellite launched a satellite called Remove Debris, which tried a couple of things. It tried to harpoon the space debris, and it tried a net to wrap around an inert tumbling satellite and reel it in. And Astroscale is using a magnetic plate that the satellite has to have installed at launch, and then you go up and catch it with the magnetic plate and reel it in that way. And so there are a number of so we're at the stage now where people have stopped talking about it and have started, let's actually test the technologies in orbit and see if we can, and see which ones are the best. What we haven't had, none of these companies have yet actually removed an existing piece of debris from orbit. That's going to happen in the next few years. And there's big space law problems associated with a lot of the biggest, most worrying objects are old Soviet stages. So if you're going to remove them, you've got to get the Russians to be part of your team and buy in. Otherwise, you're, potentially, it's potentially an act of war if you remove even one of their junk pieces from orbit. And so there's a lot still. We're still a long way from operationally removing space debris, and so I think these companies have got a lot of investment to do, a lot of building up to do before they're at the point of being able to make a profit on this. But I'm really excited that they're trying
it. One other question we had that kind of links to that was, how difficult is it to assign responsibility for whose job it is to clean up? And
yeah, that's a challenge because, again, it's the usual story that we've seen in other environmental situations, right? The polluters were the superpowers back in the Cold War, and the current actors who you might want to regulate are, from countries, developing countries and startups and so on, who might take the view that, well, it isn't our trash, so why should we pay to clear it up? And so there is a problem there. So all of these issues are again, it's eerily familiar, and from terrestrial environmental problems, and so we're going to have to address all of that.
Someone called Becca Lublin asked where you get your data from.
Right. So I get my data from a number of sources. The key thing is that the U.S. Space Force has these radars and telescopes that maintains a catalog of all the objects in Earth orbit, but it doesn't have much information on each object. And so, for example, some of the plots I have, which satellites are active, which satellites have their own engines, and so on, that I had to collect over like 40 years of digging in libraries and so on, of collecting information on every damn satellite and analyzing the orbit of each debris piece to figure out, what kind of debris piece it was, and so on. So there's a lot of effort that went into generating these plots, and so I've tried to make that all open source and public in my general catalog of space objects that's on my website. But yeah, it was not trivial to research it.
Another question was, how many objects do you suppose are still not catalogued?
Right. So in low orbit, we think we're pretty complete down to 10 centimeters. And of those, there's like, again, coming up to like 18,000, 19,000 objects in that low orbit. And there's maybe a couple hundred where we don't know quite what it is. We know it's off this type of satellite, but we don't know if it's satellite 1 or satellite 2, so there's some, but it's pretty comprehensive, down to 10 centimeters. Below 10 centimeters, we know that there are millions of tiny objects that we're not currently tracking, and yet are still big enough to really hurt if they hit you. And so that's a huge problem. And in higher orbits, the radars are not effective. They're 1/4. They're, if something is 10 times higher, it's 10,000 times fainter in radar. And so you have to use telescopes, optical telescopes, and it's not as comprehensive. So we're missing a lot of debris. We have the bigger objects in high orbit, but we're missing a lot of the small debris in higher orbit. And that is starting to improve as we deploy satellites whose job it is to look for space debris. And so, but yeah, it's it's hard enough keeping up with all the objects we are tracking right now. We're going to get, as the sensors improve, we're going to get a lot more in the next few years. But we're never going to be complete down to the millimeter size objects. But we have, I think the thing to take away is, for the larger objects, we have a very good understanding of what's up there.
How do you think space debris will affect future space science missions, and how does it affect astrophysics missions or astronomy?
Right. Well, it's a problem. When it gets to the point where it's already at the point where the probability that Hubble's mirror will get smashed by a piece of space debris is it's not high, but it's not comfortably low, right? And so as the amount of debris increases, people are going to have to dodge more and more, and Hubble can't dodge, but most modern satellites can dodge. And we're already seeing a lot of satellites having to make emergency avoidance maneuvers because of space debris. And so it's an extra thing you have to worry about. It's an extra thing you have to do. It increases the cost of your spacecraft, and it's a risk. And we could easily lose a valuable scientific satellite. Fortunately for astrophysics, the flagship satellites now are not hanging out in low orbit. They're mostly going to the Sun-Earth second Lagrange point, SEL2. Which is 1 million miles towards midnight. And they're not like exactly at L2, they're in big orbits 100,000 kilometers around L2. So there's a huge region of empty space out there with like 5 astronomy satellites and pretty much no debris. And so they're pretty safe. But for low orbit satellites, and there still are some, like for example, Corot, which is a French satellite that searches for exoplanets, they've got a real problem.
That's not great to hear, but yeah. I think the time is inching closer, so maybe as our last question, do you have any advice you would give to students or young professionals who want to go into astrophysics or aerospace or space-related careers?
Yeah, I would say for the astrophysics side, right, which I haven't talked about today, I've loved my career. You have to accept that. I mean, I went into it, there's not a lot of jobs, right? And so you have to be clear-eyed about it. I've gone through my career expecting that, I'll have another 3 years and then I won't have a job anymore or something. I've lucked out, but you have to be pretty fatalistic about it. But it has been, I've had some great moments watching Chandra go up at Kennedy Space Center, being on a mountain in Arizona, being the first person to see some weird galaxy, and so there's a lot of hard work, but it's been worth it. On the aerospace side, we were talking about this before we started, that for astronomy you really need a Ph.D. In aerospace, a master's in aerospace engineering is probably mostly enough, and there's a lot of opportunities in satellite design. I think particularly in Britain right now, Britain is finally getting its act together in space after, being. When I was your age in England, I grew up in England, and the attitude was sort of, ooh, space, that's a bit futuristic. We're too traditional. We don't do that. It would cost money and we don't like spending it. So there was not that sort of drive toward the future that I think there is starting to be now in the UK. And so hopefully, the UK will be more of a force in space going forward. It's always been, world class in astrophysics, and so there's which you can actually. Britain's been really good at figuring out ways to do world class science very cheaply, although it was nice coming to the US, having my experiments properly funded and not having to use sellotape and protractors to kind of align the telescope, but So yeah, I would say if you really want to do it, don't let anyone stop you.
I think that's very great advice and will be very useful. Thank you. And thank you
Thanks for having me
today.